work on RC. And then Yele will talk about terrestrial. And then we will do a combined Q&A session for all three. Okay. Stage is yours.
Hey. So my name is Joey, and thank you for the opportunity to share our project with you today. I'm sharing the recently inaugurated project Tor Alva. And besides sharing the project itself, I would also like to share our experience with using COMPAS RC in our project. I'm gonna start with a short video. So Torava is a fort storage, 30-meter tall, 3D concrete printing tower located in Moulins, Graubünden. The visitor will be able to enter from an existing building below the tower and walk up this spiral staircase to a platform on the top level. And the space can be used as observation and hosting cultural event on the top level. The project was inaugurated basically 1 week ago. And the last time I checked, it is still the tallest 3D printed concrete structure in the world. Yeah. So all the components are fabricated and sent to assembly hall, but basically all the printed parts are done in RFL. Exactly. This is the spiral staircase. All right. So this project was initiated by Nova Origin Foundation and designed together by Professor Benjamin Dillenberger, architect Michael Hansmeyer, and Concept Brazzini partner as a structural engineer. The development of the technology was collaboratively done by Digital Building Technology with Dr. Anna Anton on the 3D concrete printing fabrication, CSBD led by Professor Walter Kaufmann on structural engineering, and PCBM led by Professor Robert Flett on material engineering. Also, this project is partnered with ETH spinoff Saiki AG for 3D printed concrete formwork and Mesh AG for the rebar reinforcement integration. Depends on the different levels. The height of the columns varies from 2.2 meter to 6 meter. These elements are assembled in Savonnin, this assembly hall we have 15 minutes away from Moulins. Later be transported on site and stacked by a designed dry joint connection and ready to be disassembled and reused in the future. So this is the crane. The printed columns are joined together with the cast base and capital as a single element after inserting longitudinal reinforcement and grouted. And the image is one of the formwork that was used in the casted capital. And these formwork was also manufactured with 3D printing technology by Saiki. The tower is composed of 48 of these elements. Each columns are further segmented into 3 and to 13 pieces, depends on the height of the columns, with the print height of 8 millimeter. 210 kilometers of print path was printed in robotic fabrication lab in ETH Zurich within 6 months. These branching columns are designed as a load-bearing element in the structure. Additional structure tests are performed by CSPP to further investigate the compression and the tension performance of the columns. All the print paths within the design of the tower is combined by 3 layers: the ornamented layer to address on the very outside, to address the material-driven ornament, and the intermediate layer, and also the core layer that forms the channel for longitudinal reinforcement. All these print paths were generated with a numerical function that described the position of the point on the column in a polar coordination system along the central axis of the columns, the blue one you see in the image. We designed the system this way that also take into account that the geometry can be recreated anywhere, also outside of Rhino, for example, via COMPAS, and so we can utilize the supporting package that comes with the COMPAS ecosystem. The 3D printing technology shows the advantage while fabricating these V columns, these branching columns. Intersection of these branch can be nicely handled with the print path design, and in order to manufacture these load-bearing columns, horizontal reinforcement were inserted during the printing. So as you can see on the left, and the longitudinal reinforcement were inserted after all the printing is done into these designed channels and grouted. The rest of the columns remains hollow to minimize material usage and ensure material efficiency. The horizontal reinforcement were allocated every 20 centimeter. So this and the next 20 centimeter will have another one shifted between branch, so the reinforcement won't collide with each other. So basically in the whole column, the reinforcement layout is it's like on the right. Together with Mesh AG, we developed a fully automated process for the rebar integration. 2 robots work collaboratively during the process. One is printing the concrete, of course, and the other one is picking and placing the rebar into each branch when the layer reached. Yes. So with COMPAS RC, it makes it very easy for us to embed the additional information of the reinforcement to each robot target, and it informs the picking robot which diameter of the ring it should pick up, on which rack, and on the target layer which the reinforcement is needed. The placing robot can ensure the position and velocity of the printing robot through feedback and actuate itself at the right timing to avoid collision between 2 robots. But yes, all the glory, but of course we didn't start from that. We start from this. As you can see in the image, one of us is holding the pendant, the other one is holding a rebar ready to place it into the print. We have to press, of course, position and press the ring slightly into the print, and of course, avoiding hitting the robot. Since the core of the columns are not cylindrical, the diameter of the rebar rings alters. We designed this rack in a very manual way to sort the rings in order regarding the position of them in the columns, pick them up one after another through the printing process. But still, there's this problem of when is the right moment of placing these reinforcement. We cannot count these layers that we have printed to determine when to put the rebar. So the robot have to speak.
Insert rebar 480 on branch 2. This is layer 55/249.
So we added a text-to-speech engine to our production code while executing RC command. When the robot reaches a certain target that is predefined, the speaker will play this information to the operator that where and which branch to put the rebar, and also how many layers that we are away from ending printing day. Knowing how we can utilize COMPAS RC to solve our problem during fabrication, we are able to integrate these additional information during the design phase. So while planning the print path, we also plan these reinforcement information packed together and sent execute by production code we have. This red part, the additional text-to-speech engine, are added to the loop and to auditorily inform the operator when to insert the reinforcement. Surprisingly, for the automation of the rebar, things are not so different from previously. Instead of activating a text-to-speech sequence, all we have to do is launch a different sequence that send robot instruction to the second robot. The flexibility provided by RC makes it very easy for us to integrate this workflow without major changes to the pipeline we have. That is also why we are able to improve our workflow during the production of the actual columns. In the end, I want to share a piece of code for our brake check routine that we have to do every morning. This shows, how easy RC is to use for us. And also we injected a little user-friendly text-to-speech pep talk every morning for us to tell us we are very close to finishing the project. Without all the support from the people and the tool that is made available for us, it will be much difficult to realize this project. Thank you so much.